Good morning. Thanks for having me speak. This is an awesome conference and it keeps getting awesomer. All right, so I'm talking about preconditioning divergence conforming discretizations of Stokes. This is work supported by the NSF that I work on at Tufts with James Adler and Scott McLaughlin, who abandoned me for Canada. So we're going to write our Stokes system like this using there we go, using the symmetric gradient formulation. And so we've got our fluid velocity U, our fluid pressure P, and then we're looking at a constant viscosity case here. We're just going to show some proof of concepts for the algorithms and things, so we can expand this all later. So we're going to have some boundary conditions. The outward flux of the velocity is going to be 0 on the entire boundary, and then we constrain the strain rate tensor like that. All right, so we need to discretize our Stokes equations, and so there's an if-soup condition that you can read about in any of these papers. So a lot of people will choose P2, P1 if you're on triangles, or Q2, Q1 if you're on squares. This is called the Taylor-Hood discretization. It's a if-soup stable discretization, but it doesn't ensure that you have strong incompressibility or that your mass is conserved. So if this is an issue, which it might be for certain people doing multi-physics, where if you don't solve that conservation of mass equation correctly, it will fudge with your other physics that are going on. You can choose these elements called BDM1 P0 elements, where basically what happens is that on the element scale, weak incompressibility ensures that you have strong incompressibility. And so this is these BDM1 elements are floating triangles where they have a continuous normal direction, but not necessarily a continuous tangential direction. And so we enforce tangential continuity with a DG. So in the weak form, we get this kind of nasty looking thing where this is the typical thing you'd expect to see with Stokes, and then this is all the stuff that we need to add for the DG, and this B is the typical bilinear form for that. So after discretization, we get this saddle point matrix, and you'll note the 0 on the diagonal there. Because this is a if-soup stable method, we don't need a stabilization term. So F here is our discrete vector Laplacian operator. Given our boundary conditions, it's an SPD matrix. And then B transpose is the discrete gradient in this top row, and B is the discrete divergence. And so if you're familiar with the Taylor-Hood discretization, this F ends up looking like two scalar Laplacians on a diagonal. These BDM elements are vector elements, and so this is a fully coupled vector Laplacian. So to solve these systems, we're going to use a Krylov method, either MinRes or GMRes. And we're going to use a preconditioned version of these. So there are a couple of preconditioners that are very specialized to this discretization that are in these two papers. The two papers show very nice iteration counts and things like that, but they don't really touch on timings or anything. And at least this paper, the top paper here, mentions that you can do all of the typical things that you'd expect to see for Stokes, but they aren't going to look at that in that paper. So we decided to look at it. And that's exactly what we're going to do. We're going to look at a block factorization preconditioners and a monolithic multigrid preconditioner. So I made this map because ends up being an exceedingly massive parameter space when you're just looking at all the different things that you could think about trying. And I am not in any way claiming this is all the things you could think about trying. But all right, so we're going to do block factorization preconditioning. So you either have a block triangular preconditioner or a block diagonal preconditioner. And in those, you need to precondition your vector Laplacian. And in order to do that, we're going to use what we call velocity multigrid, just to contrast to monolithic multigrid, which is on the whole system. And within that multigrid method, you can look at different coarse grid operators. You can either rediscretize your problem on coarse grids, or you can use Galerkin operators. And then there are several versions of relaxation. These Venko, like an extension of a Venko method or a reduction of a Venko method, which is a block Gauss-Seidel method. Or you can just look at the point versions. And then monolithic multigrid, because I can, we're going to zoom in. And again, here we're going to look at the coarse grid operators, rediscretization or Galerkin. And then we have all of these different relaxation schemes that we can consider with the Venko methods. We can extend the Venko methods to get a little bit more robustness. And then the other class of relaxation methods that Scott talked about on Monday are these Brace-Harrison methods. So, whoa. All right, so let's start by talking about monolithic multigrid. So we're gonna fix our grid transfers. And we're just going to do geometric multigrid, standard finite element interpolation operators, and then R equals P transpose. And we're going to consider the two different, well, actually, we're only going to consider Galerkin operators, but we're going to see that they tend to have some problems for this problem, and so we're going to look at rediscretization results as well. And then what we're really comparing here is the relaxation scheme. So as I mentioned briefly, full Venko is this overlapping block Gauss-Seidel method. W transpose gets you down to a block locality, and V brings you back to a global problem. In practice, V and W are the same for this problem anyway. So basically, we're going to loop over all of our blocks. Our blocks are going to be indexed by a pressure degree of freedom. So this is going to locally enforce an incompressibility constraint, because you can think about looping over all of the rows of this B matrix. And the structure of each Venko matrix is the same as our global matrix, but how do we form these actually? So we start with our system matrix, and then we have look at a row of our incompressibility constraint. You can see, if you look really, really closely, that there are 6 little dots there. It means there are 6 velocity degrees of freedom in that row. And so we're going to pull those rows and columns, and that's going to give us a 7x7 matrix. And so you can also think about doing diagonal Venko, which is just a sparser version where you pull the blocks in exactly the same way, but you just eliminate the off diagonals in that blue block. So geometrically, this is the same as looking at the pressure degree of freedom floating on your P0 pressure, and then the 6 velocity degrees of freedom that are associated with your triangle. And to get a little bit more robustness, you can think about extending this block a little bit, which makes some sense because the DG coupling actually expands your stencil quite a bit. And to do that, we just look at the degrees of freedom on the triangles that share an edge with the triangle that has the pressure on it for that block. So this becomes a 19x19 block instead of a 7x7 block. All right, the other relaxation scheme we can look at is these Brace-Harrison methods, which have already been discussed on Monday, like I said. For this problem, we're going to consider a diagonal approximation to C, or a block diagonal approximation to C, where the blocks are the 2 degrees of freedom located on an edge. So just a little bit more coupling. So the update, then you can look at it in a block factorization form, and you're doing updates that look like this that require a solve with the Schur complement here. And so we approximately solve equation smiley face just using a single sweep of SGS, but you could do any solver that you want. Jacobi, for example, or V-cycles, whatever you'd like to do. All right, so now we're going to consider block preconditioners instead of monolithic multigrid. And the primary difference here is we're just doing multigrid on the lambda block here, which is a preconditioner for F. And lambda inverse is a V cycle, because if you turn a lambda upside down, it's a V. Yeah. Thought. And then Q is the pressure mass matrix here, which is spectrally equivalent to the Schur complement for stable in-soup stable discretizations that was shown in this paper. So in this case, we're going to do basically the same ideas as before for multigrid. We've got geometric multigrid, finite element interpolation, R equals P transpose. And you could think about looking at Galerkin or rediscretization. For the results I'm going to show, it's all Galerkin. And then you could think about doing classical iterative methods like SGS or Jacobi on this block. Or you could think about pressureless Venko, since we're just relaxing, since we're just preconditioning the vector Laplacian, you don't have a pressure, but otherwise you choose the same block as before. So for our test problem, we're pulling a test problem from the paper by Blanca and Ludmil and all these people. That's this test problem. They start with this equation, and then they just take U as the grad perp of phi. And we're going to look at it on a square domain where we have 2 to the n by 2 to the n squares. And then we're going to divide each square into triangles. So that's why you get the factor of 2 sitting in front. And so we're going to go from a 32 by 32 grid up to a 512 by 512 grid. And then we're looking for a relative residual reduction of 10 to the minus 6 for our stopping tolerance. So we're pulling finite element discretization information and matrices out of Phoenix, and then all of the solvers live in / next to / tied in with Trilinos in whatever way I had to do to get it to work for me. So again, we're going to kind of cover most of this map of different preconditioners. I know it's a lot, but I'll go as slowly as I can. So let's start again with the results from monolithic multigrid. We've got our 2 classes of Venko, or of relaxation. We've got Venko and Bracerasin, and of course several different flavors of those. And so we started with a 2-level method because it's easy. And everything was basically all hunky-dory with 2-level. And so we kind of know that 2-level convergence implies that W cycles will work for us. We haven't done all the legwork to make sure that I can get rid of those quotation marks, so they're in there. All right, so W cycles look good. This is using that extended Venko method with W cycles, and I mean, we get convergence in 6 iterations on every grid. There are 5 dashed lines there. They're all lying on top of each other. Oh, and sorry, we're looking at an under-relaxation parameter for that, for the Venko updates. And so basically, no matter which parameter we choose, we get really good convergence for this scheme. And if you look at the diagonal extended Venko, again, you're getting convergence. It now takes more iterations. I think it's around 20 iterations, because again, you're using sparser blocks for your solve, but we still get really good, relatively grid-independent results. And then you can look at doing the algebraic blocks with diagonal Venko as well, and that seems to be working well. Unfortunately, something weird happens when you go to the full blocks, and bad things start happening, and Trulino spits out loss of accuracy, errors, and my parameter tables have a lot of frowny faces in them. So we think currently that this is probably some kind of incompatibility with the Galerkin operators and the relaxation scheme that we've chosen. That would be what multigrid theory would suggest anyway. And so this is because our Galerkin operators are not equivalent to the rediscretized operators like they would be for a P2, P1 operator, or discretization, yeah. But rediscretization helps this problem. This is the same thing. This is full Venko, W cycles, but now we're using rediscretization instead of Galerkin. And this brings everything back into a nice, happy regime where we can get, with the right parameter choices here, we can get convergence in 10 iterations or so. And even the V cycles in this case are okay. We were having problems with V cycles and Galerkin where nothing was scaling, but going to V cycle multigrid here, this seems to work. Brace Harrison is kind of the same story. This is what all of the Venko V cycle pictures look like too. And then if you go to a W cycle, you get nice lines lying on top of each other. And again, this is now taking like 30 iterations instead of 10. But basically the message here is that it's complicated. There's a lot of different choices being made. And some things tend to be better. W cycles tend to be the way to go. There was that case of full Venko I showed that is obviously an exception. Extended Venko really helped make everything more robust and make the iteration counts look better. Brace Harrison is good with the W cycles again. And no matter what you do though, whether it scales or not, the best you can do in terms of your parameter choices is pretty insensitive. So that's good. And then just a quick note on timing. We see that Venko methods tend to be very expensive. This is overlapping Block-Gauss-Seidel, lots of residual updating going on and what have you. But the Brace Harrison methods can be really, really fast because you're basically doing mathvex. All right, so now let's look at our block diagonal preconditioner. We don't get as nice grid independence here, but it's still pretty fast, as you'll see later. And again, we had to use W cycles here. If you want to get nice scalable results, Venko is the way to go, full Venko anyway, but again, it won't give you a nice timing because block overlapping Gauss-Seidel. And then diagonal Venko, again, you lose some of the scalability, but still nice looking numbers. And then we can go to the block triangular method. And again, the full Venko is the clear winner in terms of iteration counts and scalability and everything. But these plots look very much the same as the block diagonal approach. So in here we have timings. We can think about doing 1, 2, or 3 W cycles as that application of lambda. And you see that you don't really, so you gain a lot in iteration counts, which I realized I didn't put here, but the cost of doing those W cycles doesn't quite work out. So doing 1 W cycle costs you more iterations, but less time. And you see the same thing is true for the Venko methods. So who wins? This is just total time to solution of all of the different methods. You can see that monolithic multigrid diagonal extended Venko takes a really, really long time. All of the Venko bars are sitting high. But the Brace-Sarrazin method, the monolithic multigrid Brace-Sarrazin method, is around 38 seconds, and as is the block preconditioning with the block diagonal method with Gauss-Seidel here. So, yeah. So classic preconditioners can be made effective. There's some problem with the Galerkin grid transfers when you use V cycles. W cycles are able to alleviate some of this. And then it's a matter of 1/10 of a second or so, but monolithic multigrid with Brace-Sarrazin relaxation did give us the shortest total time to solution here. And so some things we were thinking that might help V cycles work better are choosing level-specific relaxation parameters. Or you could just consider maybe Galerkin is not the way to go and we can do something more intelligent. And then we'd like to expand this to multi-physics applications. And yeah.